Hi, my name is Frank Chen. I'm a partner at Andreessen Horowitz. And what we want to do in the next half hour is explain one of the biggest technology shifts that's happening in our industry. The firm is now coming up to its seventh year anniversary, and we've been busy investing into some of the biggest technology platform shifts in our time. So, in that short time period, mobile and cloud were two dominant technology platform shifts that have created tons of great opportunities for us. We think artificial intelligence, and in particular deep learning, could be as profound and maybe even bigger. So we wanted to share why that is. But before we can understand why that is, we got to understand what it is. What is artificial intelligence? What is machine learning? And what is deep learning? So let's get right into it. Silicon Valley's buzzing. All of a sudden, seemingly out of nowhere, artificial intelligence is dominating the R&D agendas of the most important companies in Silicon Valley and outside of Silicon Valley. Looking at Sundar and Mark Zuckerberg at Facebook and Robin Lee, the biggest CEOs have all of a sudden said machine intelligence, artificial intelligence, deep learning are the heart of what we're doing. It's guiding my R&D agenda. Sundar has said we went from a search first company to a mobile first company. Now we're an AI first company. How in the world did this happen? And what is the shift that's happening? So, to understand the history, we have to go back in time. Luckily, the history of artificial intelligence has a clear birthday in the summer of 1956. So, it turns out people have been dreaming about creating machines that could act like humans or exhibit human intelligence. So, the Greeks had statues that would come to life. Most ancient civilizations, the Chinese, the Egyptians, created mechanically driven automatons that would behave like humans. In fiction, we have Mary Shelley's Frankenstein. All of this feeds the human impulse that maybe as humans, we can create things that behave like humans. But for the purposes of artificial intelligence, the birthday can be marked in the summer of 1956, when a group of researchers came together at Dartmouth to kick off a series of research projects whose explicit goal was to program computers to behave like humans. So we had Marvin Minsky, John McCarthy, Claude Shannon, Nathaniel Rochester all come together this summer in Dartmouth and say, let's do research. And the aim of the research is creating an artificially intelligent being. So from the point of view of the academic discipline, which is a subdiscipline of computer science, this was the birthday of artificial intelligence, summer of 1956. So what did they set out to do? The research agenda basically said, computers are sophisticated. People are sophisticated. Let's see if we can program computers to do the kinds of sophisticated mental tasks that people can do. So let's see if we can teach computers to reason. In other words, to do things like play chess or solve algebra word problems or prove geometry theorems or diagnose diseases. So all of these are reasoning tasks where you're presented with a problem and you reason your way to the answer. Here you see Deep Blue playing chess, and this was the prototypical reasoning system that we tried to design. Another thing that we tried to teach computers to do was to represent knowledge about the real world. So, in order for conversations to really understand and interact with people, they would need to understand and interact with the real world. What are objects? What are people? What's language? All of these things would need to be programmed into a computer. And in fact, specific computer languages like Lisp got invented for this exact purpose. What you see here is a picture of John McCarthy, inventor of Lisp, trying to teach computers about things in the world. The third thing that we would need to teach computers to do is understand how to plan and navigate around the world that we live in. So how do we get from place A to place B? How do we understand where doors are and what paths are and where it's safe to go and where it's not safe to go? If there are multiple ways to get to a destination, how do we choose? So these are all planning and navigation tasks, and we would have to teach computers how to plan and navigate. Here you see a picture of the first self-driving robot, if you will, invented at SRI in Menlo Park in the mid-1960s. You can see a set of cameras and wheels, and this was the very dawn of trying to program computers to plan and navigate around the real world. Another thing that we would want to teach computers how to do is how to speak language, how to understand language, how to create sentences, how to understand the context of sentences. You and I use language every day to convey thoughts and feelings and observations about the world in an incredibly subtle and powerful way. The goal is let's teach computers as much of that as we can. This is a picture of one of the very first natural language processing experiments run at Georgetown. And I'll have a little more to say about what's going on in this picture, but it was an IBM mainframe, and we were trying to translate English to Russian and Russian to English. And I'll tell you a little bit more about that later in the podcast. So, another thing that we would need to teach computers is perception. How do we see things in the world? How do we hear things in the world? How do we feel things in the world? In order to get to human intelligence, the team at Dartmouth surmised, we would need to teach computers how to perceive things through sight and sound and touch and smell. The most tractable problem to solve first, we thought, was sight. So here you see a picture of Marvin Minsky at his lab at MIT. You see this robot get up with a bunch of blocks and cameras. And this was the very first set of experiments that we would run to see if we could feed video input through cameras into computers and have them understand, aha, here are a bunch of blocks and cubes, and the big block is sitting on the little block, and I can move a pyramid onto the top of the big block. And the hope was if we could teach computers all of these discrete parts of human intelligence, so representing knowledge about the real world, speaking language, reasoning logically, that a sort of generalized intelligence would emerge from this. So we would get a whole bunch of human behavior that wasn't explicitly programmed. So things like emotional intelligence or intuition or creativity. And so the hope was that eventually, out of building all of these building blocks, that we would get to a fully autonomous, thinking, interacting robot, kind of like C-3PO in Star Wars, which is kind of indistinguishable from a human intelligence. He can move, he even has neurotic quirks. So the hope was that if we taught computers all the basics, that generalized human intelligence would emerge. So that was the goal. Hugely ambitious goal in the summer of 1956. You got to remember the state-of-the-art computer those days was a mainframe using punch cards as the interface. And so these guys who came together in 1956 were really visionary. So what happened? So what happened was a series of boom and bust cycles where people would produce this super compelling demo, and it would attract a lot more research, a lot more funding, startups, and then those things would run their course and they'd bust. You'd get to some deep disillusionment about how realistic that we could make an artificial intelligence. And these boom bust cycles didn't happen just once. They happened 6 or 7 times. I'm going to take you through a couple examples just to show you why people got so excited and then why people got so disillusioned. And in fact, this sort of boom bust cycle has a name all of its own. They're called AI winters. And you got to remember, this happened in the 1950s, started happening in the 1950s. And so AI winters were explicitly a descendant of nuclear winters, which is, gee, after a nuclear attack, nobody can live for decades in the spot where the radiation is still strong. And this was the direct analogy, which is, wow, AI research is so screwed up that we're never going to get any more progress. So funding dries up for years and years. So let me take you through some of these boom and bust cycles. So the first boom and bust cycle happened around machine translation. I showed you the picture earlier of the mainframe. Let me put this in context. It's 1954, and we want to translate desperately from English to Russian. So this is the height of the Cold War. We're coming out of the Korean War. We're headed straight for the Cuban Missile Crisis. Not a lot of native Russian speakers living in the country. And so wouldn't it be awesome if machines could translate from English to Russian and Russian to English? And so this was exactly the experiment we ran in 1954. Researchers at Georgetown University and IBM demonstrated the very first system that was capable of doing this. They took 60 Russian sentences and they translated them into English. And the demo went fantastically. For the 60 sentences they chose, the system did great. It was literally a punch card demo. So a punch card operator would punch the Russian sentences into the decks. The computer would process them. Out would come a separate set of punch cards with the English translation. And for the 60 sentences they chose, it was credible. So this set off a whole generation of research and corporate R&D spending trying to get to generalized translation systems. Now, it turns out This is an incredibly hard problem, and let me give you the textbook example. So imagine like you took a normal English sentence. This one happens to come out of the New Testament. The sentence is, "The spirit is willing, but the flesh is weak." A lot of these early systems, you would feed that sentence into the English Russian translator. And then just to verify that you got a good translation, you would do the reverse, feed it into the Russian English translator. Out of these systems, with that English sentence, "The spirit is willing, but the flesh is weak," here's a very typical example of what you would get. "The whiskey is strong, but the meat is rotten." And if you think about it for a second, it's so obvious why that translation happened, which is that's a pretty good word by word translation. And it's also obvious to a native English speaker that the translation is completely wrong. It didn't capture the meaning, what a computer scientist would call the semantics of the sentence at all. It did more of what a computer scientist would call a syntactic translation, a word for word translation. And for word translation, it's not bad. But if you had enough of these errors in sentences, you would completely garble the sense of a body of text. And this is what led to the first AI winter, which is the disillusionment around being able to capture what you really mean as opposed to word by word translations. People were very discouraged about the prospect of computers being able to do this because you'd have to understand context, you'd have to understand idioms, you'd have to understand all of these things that aren't in the words of the sentence. And this led to the first AI winter. In fact, a federal committee called the Automated Language Processing Advisory Committee said that machine translation progress was so slow that we really shouldn't spend more money. It would be spending good money after bad. Let's just stop. So here was the first AI winter. When that AI winter thawed, researchers tried a dramatically different approach. So if we couldn't translate any language to any language, let's try to constrain the language into a very specific domain. And so what people started doing research around was called microworlds. Let's constrain the real world into a tiny microworld, and let's see if we can make more progress understanding language in that context. So a couple examples, I showed you the picture of Marvin Minsky with his pyramids and the camera system that would look at the blocks. So that was a microworld. So in that microworld, the goal was to program the system to understand sentences like, pick up a block, pick up a blue block, put the blue block on top of the red pyramid. And the system would have to figure out, well, is that possible? Can you put a block on a pyramid? Well, gee, a pyramid has a pointy tip, so you can't actually put the block on top of the pyramid. So the system would have to respond, that's not possible. Right? So that's an example of a microworld. Constrain the world into this very small world and see if we can make progress. Another example of one of these microworlds was Joseph Weizenbaum's system called ELIZA, which you'll still see taught in artificial intelligence classes around the country. And its microworld was around talk therapy, which is imagine you went to a talk therapist and you want to talk through a set of problems. So that was the microworld. So let's invent an artificial intelligence that could have a conversation like a talk therapist would. So let me give you an example of one of these systems and the output it would have. So I'm going to try to do my best Nina Totenberg here. So I've got the computer giving output and somebody typing input. All right. So imagine you've come up to this computer and you type this input. Men are all alike. Computer. In what way? They are always bugging us about something or other. Computer. Can you think of a specific example? Well, my boyfriend made me come here. Computer. Your boyfriend made you come here. He says I'm depressed much of the time. Computer. I'm sorry to hear you are depressed. It's true. I'm very unhappy. Computer. Do you think coming here will help you not to be unhappy? I need some help. That much seems certain. Computer. What would it mean to you if you got some help? Well, maybe I could learn to get along with my mother better. Computer. Tell me more about your family. Well, my mother takes good care of me. Computer. Who else in your family takes good care of you? So you see through this example that it's incredibly lifelike. You can imagine a real talk therapist saying the exact same things that the computer said. So people were super excited, which is, wow, talk therapy is a very sophisticated parsing of English language. It represents a nuanced understanding of what people and relationships and what they go through and their troubles. And you could see that the example was super compelling. But here was the problem. The problem was that as soon as you tried to talk to the computer about anything other than what a talk therapist might talk about, the illusion completely broke down. The responses were nonsensical. So let me give you an example of that. I wish to know about you. Computer. Why do you say I might want to know me? To write my report. Computer. What makes you believe to write your report? I don't understand your question. Please clarify. Computer. Earlier you said I would like to know me? Yes. Computer. Can you elaborate on that? I wish to know Eliza. Computer. How does it feel to want? Want what? Computer. Maybe your plans have something to do with this. What plans? Computer. Is it because of your life that you say, what plans? It's because of you I said that. I would appreciate it if you would continue. So you see, any other context other than what Eliza was carefully programmed to understand completely broke the illusion. The system's responses are not quite right. They're not relevant. And you can see it almost as if you're sort of playing with language. And that's exactly the lesson, which is you're playing with the syntax of English sentences and trying to trick somebody into thinking you really understood them. But really what you're just doing is rearranging the words, looking for specific keywords like mother or depression and keying off those things. And as soon as it falls off script, as soon as you say a word that's not in the computer's programming, then the illusion breaks down. And this is what led to the second AI winter, which is you had these very carefully constrained systems. They would work great inside very specific contexts, but as soon as you took one step to the right or one step to the left, it just completely broke. And this led to the second AI winter. In fact, there was a UK government report published by a guy named James Lighthill, which basically concluded that AI has utterly failed to achieve any of its grandiose objectives. So here it was, the second nuclear winter. No more funding, no more startups. All right, I got one more for you. And this is the 1980s era of expert systems. It actually began in the 60s, but startups started seriously forming around this in the late 70s and early 80s. And here was the intuition. So we failed at general machine translation. We couldn't take any arbitrary text and turn it from English to Russian and Russian to English. And then we kind of failed at these micro worlds where we were trying to mimic very basic constrained worlds from the bottom up, right? Either the block world or a talk therapist world. So here was the intuition, which is, look, if we can't teach computers from the bottoms up, it's kind of like the way we teach our kids. Maybe we should go the opposite way. Why don't we take something that's widely acknowledged as incredibly sophisticated mental behavior, like diagnosing diseases or acting as a chemist or doing what a computer systems analyst would do. Let's see if we can get into these very sophisticated domains and program them, so-called expert systems, right? So the intuition was we'd find an expert, we'd interview them, we'd try to understand their world and codify their knowledge into expert systems. And then computers could try to mimic this expert behavior. Good examples of this. In 1965, Edward Feigenbaum and Carl Jussari, by the way, Carl, yes, that Carl, the guy who invented the pill, wrote a system called Dendril, which would take the output from a mass spectrometer and identify the molecules that represented the data coming out of the mass spectrometer, and it got pretty good results. That inspired, in 1972, Edward Shortliff, also at Stanford, to write a program called Mycin, whose goal was to diagnose infectious blood diseases. So you would feed it a bunch of symptoms and data about blood, and out would come a diagnosis. And it actually got to sort of 50 to 60% accuracy, which compared pretty favorably with human doctors performing the same diagnosis. And so people got pretty excited about this, which is, hey, if we can take this highly expert behavior and turn it into a set of rules that the computer could process, maybe we could just write a couple hundred expert systems. And this is actually where my own personal story interacts with this arc, which is in the late 1980s, I was at IBM, my friend Reid Hoffman. And we were writing at IBM this thing called the Integrated Reasoning System. And the Integrated Reasoning System was an expert system development tool. So it really represented the enthusiasm of the time, which was, this is going to be the path forward for AI. We're going to take these very constrained, highly expert behaviors, and we're going to build an expert system around it. And then presumably the next expert system would be a little easier to build. And let's just keep on iterating. If we write 1,000 of these, we'll get to full artificial intelligence, right? Let's bottle up the expertise of a chemist and a doctor and a school teacher and a math teacher, and away we go. And IBM's investment at the time, where Reid and I were interns, was this is absolutely going to happen. And so what we're going to need is an expert system development tool. In other words, software for developers building expert systems so that we could stamp these out very quickly and we'd get to the promised land on this approach, one expert system at a time. There were a bunch of startups that got created at this time, most notably Symbolics, which was a Lisp machine. Remember, John McCarthy invented a programming language so that we could codify language and expertise. And Symbolics was native design from the ground up to run Lisp. The community was super excited that this was absolutely the path forward. Unfortunately, what happened was that building one expert system didn't really give you a leg up in building the next expert system. You'd still have to go through this very long process of finding an expert, understanding what they do, programming the set of rules, and you didn't get a lot of leverage when you try to do that for the next expert. And this led to the collapse of expert systems, most dramatically with the collapse of the company Symbolics in 1987 and the third AI winter. So we've had these three boom and bust cycles. If you read the Wikipedia entry, there's actually more, but I just wanted to give you a taste for the boom and bust cycles that have happened. But very recently, we hit a breakthrough, and I want to describe this breakthrough to you. So what is this breakthrough? The breakthrough is called deep learning, and it's one of a class of machine learning algorithms. Let me just set this up. So a lot of the previous techniques that I talked about were attempts to program the computer by trying to figure out how do experts behave or how do humans behave, codifying those as rules, and then basically just inputting them into the computer. By contrast, these deep learning techniques feed data structures modeled on the human brain a bunch of data. And then there are algorithms that help the computer learn based on that data. So it's the complete opposite approach to the approaches that had been taken. The ideas originated in the 1940s with two researchers named McCullough and Pitts, who proposed this idea of modeling data structures and algorithms on the human brain, what we'd call a neural network today. Based on those ideas, many researchers elaborated, improved on those ideas to make the algorithms faster, to make them learn better, to make them more accurate, and to make them make better predictions. So since I'm not trying to do a comprehensive history here, let me just refer you to a couple good historical sources if you're curious about the list of researchers that contributed to these ideas, and we'll leave you the link in our text. But a couple stories along the way just to give you the intuition. So Jan LeCun, who now runs Facebook's AI lab, used these neural networks to try to recognize handwriting of zip codes. So think about how useful it'd be for any postal service if you could take a handwritten address, including a zip code, and automatically extract the numbers in the zip code. Jan did this work in the late 80s. Picking up from that, Geoffrey Hinton and Yoshua Bengio. Jeff now is part of Google's AI research team. Yoshua is with the University of Montreal. Worked on elaboration of these neural networks called deep belief networks. And their research led directly to what you use every day in Android if you talk to Android. So the speech-to-text algorithms that are in Android are direct descendants of some of Geoffrey Hinton's and Yoshua Bengio's work. Another very important figure who made significant contributions in this area of neural networks is a German researcher named Jürgen Schmidhuber, who contributed this idea of this funnily named data structure called recurrent long short-term memories with deep feed-forward neural networks, right? So these are funny researchy names, but these are all essential elaborations and improvements on this basic idea that says, look, your human brain is organized in a particular way. There's neurons connected to other neurons. So why don't we write our data structures and our algorithms to try to mimic the structure of the brain? So continuing down the path of the history of neural networks, so the basic idea, again, is let's have computer algorithms and data structures that mimic the human brain. And Google decided to run an experiment. And as you might expect, when Google gets into the game, the contribution they bring to the table is scale. And there's two dimensions of scale here in the experiment that Google ran. One dimension is around data. And so if you're Google and you want to feed some neural networks data, you have a lot of assets. You have people's emails, you have search results and search queries. But what Andrew Ng, at the time he was a Stanford professor who worked on this research, used as data was YouTube videos. So he got 10 million YouTube videos. He took 200 by 200 stills from those videos, and that's the training set. And then the other dimension that Google brought to the table was scale, so computational resources. Google loves nothing more than distributed computing, lots of computers with lots of cores, crunching data. And so for this experiment, he brought 1,000 computers with 16 cores, so 16,000 cores, and he would let them run for a week on these 10 million YouTube videos. So again, using the basic neural network structure, feeding it 10 million YouTube videos into 1,000 servers, 16,000 cores for a week. So guess what they found? Guess what the researchers found? Well, if you set this neural network up and feed it 10 million YouTube videos, you'll find exactly what are in YouTube videos. And the first thing you find is cats, because people love uploading videos of cats to YouTube. But of course, you find more than cats. You find hundreds and thousands of objects. And in fact, on a 20,000 object database, they recognize 16% of the objects in them. So thousands of objects got recognized by this neural network. So here's the fascinating thing. We didn't have an expert say, here's how you find a cat with nose and paws and whiskers and this shaped eyes and these funny shaped ears. We basically just fed the network a bunch of data, and the data learned to categorize the inputs without any guidance from an expert or without any rules. So this is the heart of the revolution. This is the big breakthrough in artificial intelligence. So instead of interviewing humans, trying to extract expertise, programming the computers with that expertise, it's a data up approach. Just feed it a bunch of data, and the computer will learn how to classify by itself. And so if you ask the question, gee, why are people so excited about neural networks when we've been working on this since the 1940s? The answer is scale. Comparing Andrew's experiment with Jan LeCoultre's experiment recognizing handwritten zip codes, Andrew had 1 million times more compute cycles. He's got 33,000 times more pixel data. He's got more sophisticated algorithms. If you look at what's happened with deep learning research since then, since this seminal moment in 2012, he's got a whole ton of funding, government funding, university research, startup money. And so what they started in motion in 2012 was a lot of enthusiasm around this particular type of artificial intelligence research called deep learning. So let me give you a sense of how these neural networks work by showing you a demonstration of Google's TensorFlow, which is a deep learning library. So what you see in your screen is a classic deep learning problem. On the right side, you see these orange and blue dots. Think of them as data set. It's a data set with data points. A data point might be an orange dot is spam and a blue dot is not spam. Or an orange dot is an offensive forum post, or a blue dot is a non-offensive forum post, or an orange dot is a cat in a YouTube video and a blue dot is a dog in a YouTube video. So all of these categories are represented by these dots. The job of the neural network is to draw a boundary around these dots. You can sort of see that in the blue and orange shaded portions using a neural network. So let's get started. On the left side, we have inputs where we're going to feed it tons of data, examples of these either email messages or pictures that we're trying to categorize. And then what we're going to do is build a neural network. Neural network has multiple layers. By the way, this is why we call it deep learning. Deep refers to the fact that there are multiple layers inside this neural network. So for example, I've just created a 6-layer neural network here, and I'm going to give each layer of the network a bunch of neurons. And you'll see as I add all of these neurons, the connections between all the neurons are being added, and that's the heart of the system. What's going to happen is the neural network is going to train itself, given all of the input data, to set connection strengths between each of the nodes. And so you'll see that as I feed it data, that the blue and orange lines connecting all of the nodes in the network will get darker or lighter depending on the connection strength. So what fundamentally these neural networks are doing, and I'm going to hit the go button to start feeding it data, and what you'll see is the connection strengths between all of the nodes in the network are going to be adjusted, and then the output that's a result will appear as shaded portions. And the goal is for the network to draw a boundary around the blue dots in the middle and the orange dots separately. So I'm feeding it lots more data. And you can see that the network quickly trains itself to distinguish the blue dots from the orange dots. And in fact, in this case, I needed to feed it no more than 50 or 60 iterations or data sets for it to draw that boundary. So that gives you an intuition what these things are doing, which is I haven't told the system anything about what I'm trying to accomplish. All I have done is fed it a bunch of data into this specific data structure. And the computer has itself learned how to set the connection weights between all of these nodes in the network so that it can mathematically draw the boundary between the blue dots and the orange dots. So hopefully that gives you an intuition about how these things work. So this browser-based demo does a great job of giving you a sense of what these algorithms and data structures are doing. To give you a sense of the scale, we had a couple hundred connections up on this screen between the layers of the nodes in our network. If you were to buy an NVIDIA Drive PX car computer, it would have 27 million connections. If you looked at Andrew Ng's Cat Finder, it had tens of millions of connections. And then, oh, by the way, if you're feeling a little intimidated, you'll be glad to know that your brain's visual cortex, which is its visual processing system, has 10 to the 6 times more neurons than that, or more connections than that. So we've got a while before deep learning systems will get nearly as complicated as our human brains. But it's an exciting thing to think about that we're on that path to increasing sophistication through bigger data and bigger neural networks. And so I wanted to put that in context with artificial intelligence, machine learning in general, and deep learning. A lot of people treat those terms synonymously, but they're not really synonyms. So the way I think about it is machine learning is this whole set of techniques where we're trying to program computers to exhibit human intelligence. And we talked about a bunch of those. So there's natural language processing, syntax parsing, there's search optimization. So there's a whole set of techniques. There's expert systems where we're trying to get computers to behave like humans. Now, machine learning is one of those set of techniques, and it's a peer to search techniques, constraint satisfaction techniques, logical reasoning techniques. And then if you double click on machine learning, what you'll get is a whole set of techniques there. Deep learning, rule learning, decision trees, random forest, support vector machines. So there's a whole set of techniques where we're trying to have machines learn from data. And it turns out deep learning has been the most productive and accurate of these machine learning systems. So hopefully that gives you the taxonomy. Artificial intelligence is a set of algorithms and techniques to try to mimic human intelligence. Machine learning is one of them, and deep learning is one of those machine learning techniques. Now, I want to contrast that with the things that you see in movies where people are behaving like people. So if you saw Her, or if you saw Chappie, or if you saw the Terminator movies with Skynet, those are science fiction. That's not artificial intelligence. What artificial intelligence is a branch of computer science, and deep learning happens to be the most productive technique that we've come across in the last couple of decades to try to get computers to behave like humans. Okay, so how useful is that in everyday life? Well, you happen to be using machine learning in the products that you use every day. So if you followed a BuzzFeed headline to go to a BuzzFeed article, that headline was tuned using deep learning. If you're an Airbnb host and you saw a price that the system recommended that you list your property at, that recommendation is a product of machine learning. If you use Google's photo app and you see that it's grouped the photos by a set of people, the face recognition algorithms in those Google Photos apps are powered by deep learning. If you go to Pinterest and do visual search, in other words, I love this purse or I love this lamp, find me one just like it, the visual recognition algorithms used to find you a close match are powered by deep learning. And if you go to Facebook and start having chats with the M app, their messenger app, a lot of the natural language processing that happens in there so that you get a reasonable response powered by deep learning. So you're using deep learning every day already. Because deep learning has been so productive at making applications better, we have a set of investments where the companies can help anybody who needs to put deep learning into their app even better and faster. So we have companies like Databricks and Arimo and SigOpt, all of which will help you bring deep learning techniques into your own application so that you can make your application smarter, more predictive, and ultimately more user-friendly. So where are we going with deep learning? How far can we get? And can we get to the dream of fully generalized human intelligence? Well, let's go back and revisit the original design goals for artificial intelligence. On human reasoning, deep learning has already made incredible strides relative to previous techniques. You probably saw the press coverage around AlphaGo, which defeated the human grandmaster in Go. And you might be wondering, gee, it's just a board game. How complicated could that thing be? Well, it turns out on a 19 by 19 regulation Go board, there are more possible moves, 10 to the 170th, than there are atoms in the universe, which most people put at 10 to 80 or 10 to the 82nd power. It's a Google times more complicated than chess. And because of the complexity, there's no way that you can use a traditional artificial intelligence technique like search to brute force search all the possibilities. We just don't have enough compute power to search through all the possible moves. And so you need to bring deep learning techniques to figure out which branches of the search tree am I going to actually explore. And so deep learning became the organizer of multiple techniques used to figure out which moves should I evaluate when I'm playing this board game. And in fact, what artificial intelligence researchers call using multiple techniques led by deep learning is ensemble learning or ensemble problem solving. In other words, we're going to take a set of techniques and use them to try to solve problems like the reasoning problem that would go with being a human grandmaster at chess or checkers or Go. One of the fascinating things that's come out of this is that Go games were live broadcast, and professional Go players, amateur Go players around the world were watching these games. And if you asked them what their reactions were to the moves, they would say, wow, watching that thing has really rekindled my passion for playing Go, because the way AlphaGo played Go is not like the way human players played at all. It made moves that were completely unexpected and looked like terrible moves, but turned out to be great moves. And so what's happening is there's this feedback loop that comes back with watching artificial intelligence work. So humans watch artificial intelligence do its thing in this play a Go game, and it in turn influences how the Go players play their future games because they're learning new strategies and techniques from it. In fact, Lee Sedol, the human grandmaster who got beat, said, I have improved already. It's given me new ideas. And I think this is a super important observation of how artificial intelligence systems will actually interact with humans in the real world. So there's a lot of talk about how AI is going to completely replace humans. I like to think about how AI is actually going to make humans better at what they do, and we've already seen this with the Go players. So it turns out that using deep learning techniques, we've already gotten to better than human performance on a set of tasks that you think we would need to understand the world on. So these tasks include diagnosing diseases, looking at x-rays to figure out if there are tumors in them, figuring out if there's cancer in blood, and all of these complex tasks that used to take highly, highly trained individuals. These are perfect examples of how deep learning can get to better performance and human performance because they're just taking data and they're making categorization decisions. Does this blood sample have cancer in it or not? We're going to see hundreds and hundreds of startups over time getting to better than human performance on things that we used to think only the most trained humans could do. What about planning and navigation? Well, I want to tell this story about George, who is the guy sitting in the car here. George is the CEO of a company called Comma.ai, which happens to be an A16Z investment. And he built a self-driving car all by himself. One person in a literal garage building a self-driving car. And let me put this in context. In 2004, DARPA sponsored the very first Grand Challenge in the Mojave Desert. They got 20 entries from the leading universities and startups of the time, and they set up a 150-mile course in the desert. And the leading entry, which was Carnegie Mellon's self-driving car called Sandstorm, went a total of 7.32 miles out of the 150-mile route. So that was in 2004. In 2007, DARPA sponsored the Urban Challenge, which was a 60-mile city course set at George Air Force Base. And many universities finished. CMU and Stanford took the top two spots. You could see the rapid improvement. In just 3 years, they went from, I couldn't go further than 7 miles in a desert, to I can complete a 60-mile city course. And that set off an arms race for autonomous car programs. And so every major car manufacturer now has a huge autonomous driving program with thousands of engineers. So GM and Ford and Tesla and Google and Toyota and Lyft and Uber and Bosch and VW, on and on. All of these companies have huge numbers of engineers working on autonomous car systems. Enter George. George figured out how to build a self-driving car all by himself using deep learning techniques. And that tells you how sophisticated the systems have gotten. So on the one hand, you have thousands of engineers working at the best R&D corporate facilities there are. And on the other hand, you have George riding on top of open source. And George was able to build an autonomous car that completely works. In fact, one of the people on my team named Kyle got into the car with them and drove straight down 101, no hands on the wheel, with George's autonomous driving system. So that tells you about the great promise of the sophistication of this deep learning system where one guy can build a self-driving car on top of the algorithms that are now in the open source community. Let's talk about natural language processing. You'll remember that this was one of the very first AI experiments that got run, trying to translate English to Russian and Russian to English. The community has made huge strides since then. It remains a very, very difficult problem, but deep learning and tons of data, right? Think about all the data that's on the internet today that wasn't in the 1950s, Twitter streams and Facebook feeds and blog posts and so on. We have this massive data source that we can feed into these systems to perform the complicated natural language processing tasks that we need to perform. And it's a hard problem. So as an example of that, this is a perfectly valid English sentence. Paris Hilton was in Paris at the Paris Hilton listening to Paris. Now, you might need to spend a second or two to try to parse that sentence to figure out, oh, Paris Hilton, the celebrity, is in Paris, France, the city, in Paris Hilton, the hotel, listening to Paris, the album. And now computers are getting very, very good at parsing that sentence in exactly the way you did, which is, what is Paris Hilton in this context? Here is another perfectly valid English sentence. And look this up on Wikipedia because it has its own very, very own Wikipedia page. Buffalo, 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 buffalo. It is actually a valid English sentence. That one's tough to parse, but go look up the Wikipedia page. So understanding natural language and the context and what parts of speech words are and what the sense of a sentence is very hard, and deep learning is making huge strides in helping us do that. In fact, Google just released an open source project to do exactly this, which is to identify the parts of a sentence and break it down into nouns and verbs and subjects and direct objects and so on. And go find that yourself. It's Google's famously named Parsey McParseface open source project. On perception, we are also making huge strides with deep learning. So what you see in this slide is the view of what you want your autonomous car to have, which is looking out into the street. It's identified the objects in that scene. On the left side, here's a sedan, probably moving 30 miles an hour. On the right side, we've got a biker, probably moving 10 to 15 miles an hour. Out of them, we have another car. Then we've got a bunch of stationary things like trees and sidewalks. And so you want a system that can look out into a scene like this and in real time categorize all the objects in it and make predictions about where those objects are going to be so that you can plan a route that's safe and effective. Deep learning is playing huge roles in an autonomous car's ability to understand and parse a scene. In fact, NVIDIA attributes a lot of its recent growth and success as a business to this new line of business, which is providing deep learning systems for autonomous cars. Jensen Huang, the CEO and co-founder, said, "Accelerating our business growth is deep learning, a new computing model that uses the GPU's massive computing power to learn artificial intelligence algorithms. Its adoption is sweeping one industry after another, driving demand for our GPUs." So as you can see, this is touching many, many different parts of Silicon Valley, from the silicon, literally the chips that we use, on up, and we're just getting started. Another great example of the strides that we're making in perception comes out of research from Cornell University, where they also fed the learning algorithms YouTube videos. In this case, they fed videos of people doing food preparation tutorials. It's one of the most popular genres on YouTube. And what the researchers were able to do, given all of this input, people preparing food, is basically break down the steps of the recipe into discrete chunks. So they recognized when somebody was chopping onions, distinguish from when they were mixing, distinguish from when they were running the blender. And so you could take a 10-minute video tutorial on how to make chicken tortilla soup, break it into the discrete chunks, And deep learning algorithms have gotten to incredible accuracy, being able to accurately label the discrete steps of preparing food. Now, all we need to do is marry that up to a robot that will prepare the food, and we're golden. And so here's the tantalizing prospect. Deep learning is helping us make fundamental progress on all of the original design goals of artificial intelligence, which was to mimic the many, many different facets of human behavior. And so maybe this is it. Maybe this is the path forward to generalized intelligence, to things like emotional intelligence, to things like creativity, to things like intuition. And in fact, you'll see a whole genre of AI deep learning research that is around creativity. An example of that is deep jazz, which can actually compose original new jazz compositions. And so it's working. This looks like the start of a fundamental breakthrough in AI research. The way I think about it now is that all the serious applications from here on out need to have deep learning and AI inside in exactly the same way that all serious computing systems needed to have Intel chips inside them. And Intel famously did their Intel Inside advertising campaign to drive this home. I think now about the startups that we see and the systems that are getting built that deep learning needs to be inside these systems to make them better, faster, more responsive, easier to use. And it's just going to be a fundamental technique that we expect to see in all serious applications moving forward. So we're in an AI spring. Only time will tell if this leads to the promise of generalized intelligence. But what is absolutely non controversial is that deep learning is the most fundamental advance in artificial intelligence research since that summer of 1956. It's going to make every application better and smarter and faster, more responsive to our needs. And I can't wait to see the startups that lead us there. So, this is a super exciting time, and why we think that AI and deep learning could be as fundamental platform shifts, technology shifts, as mobile and cloud were in the last 5 to 10 years.